Orthogonal projections onto one-dimensional subspace or line. Okay. So orthogonal projections, it is a linear transformation, and major applications of orthogonal projections in machine learning. The first one is dimensionality reduction, and the second one is linear regression. Okay, dimensionality reduction means if we have a machine learning system like this. Okay, it takes some parameters as input and output the weight of a person, or it predicts the weight of a person. Suppose we have the age of the person, the height, and the name of the person, and the job of the person. Okay, so it is these four are the features we are using in this application. These are the features, and it is 4-dimension because we are having four features we are using. And if when we consider these parameters, this name is totally insignificant to predict the weight of the person. Okay, name has no role in predicting the name of the person. So we can cut down or we can reduce this parameter, and so that we can reduce from 4D to 3D. Okay, so that is an example for dimensionality reduction. And what is the role of projection? Suppose we take job. So assume that the job has some kind of relation with the weight. Okay, but we want to reduce it into 2D. Okay, we want only two parameters, but we have three parameters, and I want to reduce one of it. Okay, so when we remove this parameter, there may be some error in the prediction of the weight. Okay, there may be some loss of information to the system. So in order to avoid this loss, we can map the effect of this parameter to the other two parameters. Okay, for that we can take the projection of this element of this parameter with respect to the other two. That means we are reducing it to 2D. Okay, so that is one of the example for dimensionality reduction. Then linear regression. In linear regression also we can use the orthogonal projections. Okay, so take this example. This line is actually this regression line or the function that uses to predict the value, and these dots are the original values. Okay, and the projection on this line, corresponding projection on this line is the prediction corresponding to this. Suppose this is the original weight of the person and this is the predicted value. Okay, predicted weight of the system, that is the value predicted by our machine learning system. Okay, then this is the projection. We call it as a projection of this element on this line. Okay, so what is our purpose is to reduce this error. Okay, this difference between the original value and the projection, that is called as error, and our aim is to reduce this error. Okay, so projection is used here to find out the difference between the original value and its projected value or the predicted value. Okay, so we will see these things later. So these are the two major applications of projections. And the definition for projection is let V be a vector space and U is subset of V, a subspace of V. A linear mapping pi from V to U is called a projection if pi square is equal to pi on pi, which is equal to pi again. So that means that when we project one value, one vector to a subspace, Then if we again apply another projection, the same projection on the projection itself, so this is the projection, and we apply projection on it again, we will get the same value. So that means that if you have a plane, suppose this line is the u, is the subspace, and this is the vector in space v, and if you find the projection on this, okay, so this is x and this is pi of x, the projection on this line, and when you again try to find the projection of pi of x, it will be the same vector itself, it should not change. Okay, so that is the statement means. And the projection matrix, it's again, projection is a linear transformation, so in order to do the transformation we can use the transformation matrix, and the projection matrix is the one that will give you the projection of a vector. And we can apply the same rule over here. This rule we can apply over here also. That means if you have this vector x, and when you multiply it with p pi is the projection matrix, p pi into x will give you this projection matrix. Okay, and when you multiply again with the p pi, this there will not be any change, it will be again mapping to the same projection. Okay, so that means that if you have the projection matrix and you take the square of it or multiply it with itself, we will get the same matrix. That means suppose p is this matrix, and if you multiply this p with the same p itself, okay, p into p will give you the same matrix. Okay, it will not make any change, any difference in the projection. That is projection matrix. And so for example, you take a 2D plane like this. So this the x1 x2 are the axes, and this is the subspace of the in this 2D plane. This line we name it as u. It is the subspace. It's a one-dimensional, and the plane is two-dimensional. Okay, and the base vector is b. That is the base vector of u. Then assume some vectors. Okay, all the red, these are the vectors. Okay, we have infinitely many vectors on this xy plane. In this 2D plane, we take some examples. These are the some of the examples. Okay, and take one of these vectors as x, and find the projection of x on this line u. So the projection is represented like pi of x. And how do we find the projection? We have to draw a line from this to the line. It's a perpendicular line. Okay, this is perpendicular. It's 90 degree. Okay, and this x, that means that we take the projection of x on u, and it is represented as pi of x. And actually pi of x represents x itself. Okay, but in order to represent x, this vector includes two coordinate values x1 and x2, okay, corresponding to these two axes. But to represent its projection, we need only a scalar value, the coordinate. That means any vector on this line can be represented in terms of lambda b. Okay, in terms of the multiple of the base vector. Okay, if you want to represent a vector over here, it will be minus b. Okay, and next we have minus 2b, like that. Okay, so any vector on this line can be represented as a multiple of b. Okay, so we just need this lambda value to represent any vector on this line. So if you want to represent the projection of x here, we need only a lambda value. Okay, so we are reducing it from 2D to 1D, two-dimensional to one-dimensional. And this is a vector. This vector is represented as x minus pi of x, or pi of x minus x. Okay, it's an important vector. Then this b is the base vector of u, and pi of x is the projection of x. any vector on this plane can be projected to this line u. Okay, so if we take this vector, this can also be projected to this line, and this similarly this vector, this vector, this vector, or any vector on this 2D plane, in this 2D plane can be projected to this line. So vector x is two-dimensional and its projection pi of x is one-dimensional because we need only one parameter to represent that. And pi of x represents x with a lower dimension. So pi of x is the projection of x, or pi of x represents x itself with a lower dimension. And it's called the dimensionality reduction. Okay, let's look at this video we have used. Okay, this line, and so we have taken this from this video, mathematics for machine learning PCA course. It's from Imperial College, UK, Imperial University, UK. Okay, so this video shows this pink line represents, okay, this is the vector x, and this pink line shows the distance for different projections, distance from this line for different projections, and this graph shows the distance, okay, distance of the vector from the line for each projection. Okay, so we can start from the beginning. So okay, here it is high, and when it is perpendicular to this line, it becomes the minimum. Okay, and again when it moves to the right hand side, it is increases. So projection, when you take the projection, this distance should be minimum. That is the condition. And the properties of projection pi u of x is closest to x, then the length of x minus pi u of x is minimal. Okay, the length of that vector, that means if you have the line and you have the projection, you have the vector over here, and when you find the projection, this is pi u of x. Okay, and this is the vector x minus pi u of x, that is a vector again, and this vector and this represents the length of that vector. That should be minimum when you take the projection. That's what it says. And this vector vector x minus pi u of x, it is orthogonal to this line u, or we can say that it is orthogonal to the base vector of u. So since it is orthogonal, its inner product will be 0. Okay, so this is our vector, and its inner product with the base vector will be 0 since they are orthogonal. Then pi u of x can be represented as a scalar, it's a scaled value of the base, lambda into b. Lambda is a real number, and pi is the member of, it belongs to this subspace u. Okay, and when you do this projection, we have to find out two parameters, basically the lambda or the pi value, the projection matrix. Okay, you have to find out this one or this one, then we have to find out the actual projection. Okay, so these three we can calculate. So first, how do we calculate lambda? And based on the previous rule, we can say that the vector x minus pi u of x and the base vector, they are orthogonal to each other. That means if you have the line and this is your x, and you find the projection pi u of x over here, and this is actually the vector, this one. Okay, this vector, you can represent it as x minus pi u of x, or you can represent it as pi u of x minus x. Okay, whichever is better. both are correct. Okay, then this vector is perpendicular to the base of u. Okay, so they are perpendicular, so this inner product will be 0. Then pi u of x can be substituted with the lambda b. Okay, pi u of x can be represented as lambda b. So we replace that. Then we have to remove, we have to split it into two inner products, xb. So xb, inner product of x and b, minus lambda into inner product of b and b. So that will be equal to 0. And you bring it to the right hand side, lambda bb, and finally we can reduce it into lambda is equal to inner product of x and b divided by inner product of b and b. So we can do it in the reverse order also, because they are symmetric, and b inner product of b on b is the norm value of b, the whole square. Okay. So lambda can be written like this, B transpose X. So we are taking a dot product as the inner product here. So it is B transpose X divided by B square. That is the lambda value. And if B is a normal orthonormal basis, then the length of B is 1. So we can reduce lambda like this, B transpose X. Okay. Now we have to find out the projection. Pi u of x is equal to lambda b. Substitute, substitute the value of lambda, b transpose x divided by b square into b. Then the length of the vector, okay, length of this projection is equal to lambda into b, length of b. Okay, so this pi u of x is equal to, we can write it like this. That is the value of lambda. We can substitute the value of lambda over here, b transpose x divided by b square. Okay, that we substituted here, and it is equivalent to cos omega into length of x. And how it comes, we can just check. This is our xy plane, and this is the line or the vector space u, subspace u, and this is the vector x, and we find the projection over here. Okay, and omega is the angle between vector x and the line u. Okay, and then what is cos omega? Cos omega is actually adjacent side divided by the hypotenuse. Okay, hypotenuse is the length of x. So adjacent divided by hypotenuse. And what is actually adjacent? It is the projection vector. Okay, this is the projection vector, that is this is our vector, and when we draw the vector it will be like this up to this. Okay, so this distance means length of pi u of x. This is actually pi u of x. Okay, so adjacent side means it is length of pi u of x. Okay, so what is pi u of x? That is equal to cos omega into length of x. Okay, that's what we have written here. Cos omega is equal to pi into length of x. Okay, now find the projection matrix p pi. The projection is a linear mapping. Pi u of x can be written as p pi of x. So what is pi u of x? We got pi u of x like this, b into b transpose x divided by b square. Okay, so we combine b and b transpose divided by b square into x. So pi u of x is p pi into x. So what does it mean? P means this part. P pi is equal to b into b transpose divided by b square. That will be pi value. P pi value. Okay. And b transpose is symmetric, so p pi is also symmetric. Okay, the transformation matrix should be symmetric. That is one property we have studied earlier. Then some of the remarks we can make here. The projection matrix p pi projects any vector x in Rn on to the line through the origin with the direction b. The projection pi u of x belongs to Rn is an n-dimensional vector and not a scalar. But we can represent it with a single value lambda instead of an n coordinates. We can call it as dimensionality reduction. That means we reduce one vector from Rn to a one-dimensional thing. Okay. Then we can take an example. Find p pi onto the line base onto the line with the base b is equal to 1 to 2 transpose through the origin. Then p pi, the equation for p pi is the projection matrix is b transpose divided by b square, or b transpose divided by b transpose b. So we take the inner product dot product here. And what is b transpose? We can write it like this. B is 1 2 2, b transpose, okay, multiply, we get the matrix like this. And b transpose b is 1 2 2, 1 2 2, it will give you a scalar value 9. So what does it mean? P pi is equal to 1 by 9 into this vector. Okay, so we got the p pi value. Then find the projection of x is equal to the vector is 1 1 1. Okay, then pi u of x is equal to p pi into x. So p pi we got in the last slide, and substitute it here, 1 by 9, that p pi matrix, and 1 1 1. So what we get, it is 1 by 9 into 5 10 10. What happens? It is 5 by 9 1 2 2. Okay, so that spans 1 2 2. Okay, that means that this is 1 2 2 is our base vector, and this vector, this projection belongs to the span of that matrix. So if we apply p pi on pi u of x, it will change. It will not change anything. Okay. That means this is the projection. This is the projection, and if we again multiply it with the p pi, it will not change. We will get the same answer. Okay. So that is it. And the remark, pi u of x is an eigen vector of p pi, and the corresponding eigenvalue is 1. That we will study later. Okay, that's all.